Okay, so this is where we left off on practicing this significant figure calculations. So this is from your OWL and specifically question 6. And so okay, so looking at A, when 96 or 98.750 and 90.3 are divided, the answer should be based off of. So when we're multiplying or dividing, we're talking about sig figs, specifically the least amount of sig figs. So first, let's identify how many sig figs are in 98.750. So all non-zero digits here count, plus the trailing zero, because it comes after a non-zero digit as well as a decimal. So here we have 5 significant figures. Here we have 3 because that 0 is sandwiched. So when we're multiplying, dividing, we want to make our calculation or our answer to the least amount of sig figs in the equation, which here happens to be 3. So our answer should be based off of 3 significant figures. So when I put this into my calculator, I get 1.09357. We run around this to 3 sig figs. So 1, 2, 3 sig figs. And we don't happen to have to round that 0.9, or I'm sorry, that 9. Because after it's a 3, so it's good how it is. Next, we're looking at the same 2 numbers, but this time it is subtracted. So when we're doing addition, subtraction, we want to go with the least amount of decimal places. So the answer should be based off of decimal places. And so here, this has 1 decimal place, where this one has 3. And therefore our answer should be based off of 1 decimal place. So when I put this into my calculator, I get 8.45, and we want to round to only 1 decimal place. But this does make that 4 go to a 5. So looking at the next slide. So moving on to chapter 2, talking about atoms and molecules. So what is an atom? So I love to start with definitions. So the definition is a basic particle of a chemical element. And it's unique to each element. So here is a picture of an atom, right? With this being the center or the nucleus, and everything surrounding it. Let's see, can we do a highlighter? This is the electron cloud. Which we'll get into more detail in a second, but I just wanted to introduce that to you. So if we were talking about an atom of gold, we can't see it with a naked eye. We can't see gold with well, an atom of anything with the naked eye. So here's what we can see, this chunk of gold. And if we were to zoom in, like with a crazy, crazy high resolution microscope, we'd be able to see all these little dots here. And even this picture doesn't really show individual atoms, but there'd be lots of different atoms in there, which all would look like this with a nucleus or a center and some electron clouds. So over time, we've learned more about the atom. So it first started off as just this idea that it was the smallest unit and it was indivisible. And then J.J. Thomson said, I don't know if it's necessarily the smallest unit. I think it has subatomic, meaning smaller than an atom, particles. And so those are what the chocolate chips represent. And then along came Ernest Rutherford, and he said, yeah, I agree. But I think these particles aren't just randomly put everywhere. I think specifically there's the nucleus or a center and an outside. And then Bohr, which might be a name you recognize, came along and said, yeah, I think the outside that you're referring to, Rutherford, is these orbitals. And I think electrons, which we'll get to in a second, only exist in these orbitals. And then we reach present day, which says, not necessarily. I think the electrons more so hang out in a cloud. So the modern view of the atom by Erwin Schrödinger is also called the quantum model. And basically there's a lot on this slide, but basically what I want you to take away is that there are these clouds, and these clouds kind of hang out like Saturn's rings, where the electrons exist and they move. So this is this orange here isn't millions of electrons, but rather the path of one electron. And so that's why they got it a cloud. They call it a cloud. So these subatomic particles, right? So they are particles that are smaller than the atom. So here's our modern view of the atom. We have protons, which I'm sure you've are familiar, neutrons, Jimmy Neutron, and electrons, which I was just talking about previously. And so basically, if we were to break this down, create ourselves a little graph here, location, charge, weight. Protons are in the center. They have a positive charge, and they're pretty heavy. I mean, not heavy, but like heavy in comparison to the electron and the neutron. So the neutron also hangs out in the center. It doesn't have a charge, though. He is neutral. He is Switzerland. And he is also heavy. The electron hangs out in the cloud, has a negative charge, and in comparison is kind of light. So this is, oops. So this is different for every element. Maybe, let's say we have element A. He's going to have, X amount of protons. but element B is going to have Y amount of protons. And the makeup of these subatomic particles is what makes each element its own element. So when we're looking at the periodic table, right, we see something like this. We see the symbol. Some periodic tables would even say hydrogen down here. They give you the name. You see this atomic mass, which we'll get to a little bit. Oh, the name is right here. I'm so stupid. And then the atomic number. So this number is unique to each element, but it also corresponds to the number of protons. And so this is what makes every element unique, the number of protons. So if I were to change the number of protons, I'd be changing the element. So the atomic mass, what the heck is this? For definition's sake now, it's the average mass of all the isotopes. Okay, and you're like, Kayla, what the heck's an isotope? We'll get there. So here's what the periodic table looks like. This is a periodic table from a different textbook, but I often refer to the periodic table, when I just need to look up certain things. I go to ptable.com. It's one of my favorite periodic tables. I'm not going to pull it up for you right now, but it's like awesome. If you hover over the element, it gives you like all of the properties, and like it'll even do its own electron configuration for you, which we'll get to later. But it's just cool. Highly recommend. And obviously it's digital. Yes. So the periodic table, right? These are all the elements that have been discovered. And if you notice, they're organized by atomic number, which happens to be organized by the number of protons. Organized by the number of protons. Cool, right? So, oh, here's a link to that P table. So I talked about isotopes earlier. So what is an isotope, right? So typically, I'm sorry, let's clear this. So typically, your number of protons equals your number of neutrons equals your number of electrons. And that would be different for each. I don't write typically. I don't want you guys to get too caught up in that. Typically, But isotopes are these special cases where we have a different number. I don't like that. Different number of neutrons than protons. So basically, when P does not equal N. Okay, so here's some examples. Carbon 12, carbon 13, carbon 14. Carbon always has 6 protons because that's what makes it carbon. But we change from having equal numbers of neutrons to all of a sudden having different. And if we also notice, there's a trend here that changes seem to increase our mass number every time we add an additional neutron. So if you remember me saying that protons and neutrons, they were heavy in comparison, well, that's because together they contribute to the mass. So P plus N equals the mass. So if we look here, 6 protons plus 6 neutrons, oh, it has a mass number of 12. 6 protons, carbon-13 has 6 protons, but 7 neutrons, and a mass number of 13. So to define what we've learned so far, right? Atomic number is the number of protons. The mass, or mass number, is the number of P plus N, protons plus neutrons. And we haven't quite got to this, but I'm going to foreshadow this a little. The charge is your protons minus your electrons. So we're looking, here's just a little slide I thought was interesting because you're like, what the heck's an isotope? Well, there's different isotopes in nature, and sometimes that can tell us how old certain elements are. So there's like carbon-14 here, right? And it shows us that this is really old groundwater. Yeah, I thought that was kind of interesting. Anyways, so I have the definition of isotopes up there. So here's what we normally see. I'm sorry. So here's what we see sometimes, not necessarily on the periodic table, but this is a notation that we should get ourselves familiar with, where we have listed the symbol for the element, its mass number in the top left, its atomic number, which doesn't always have to be written, right? Because these always correspond to each other. And they always, if it's helium, it always has 2 atomic number. Its atomic number is always 2. And just a reminder here, atomic number is the number of protons, right? If it's magnesium, it always has 12. And then we have charge here, which I was talking about earlier. So this is written a little bit differently than the periodic table, but it's a notation that we should get used to here. So ions are when we have a different charge than 0, right? So remember when I said the charge was P minus E, protons minus electrons? So for instance here, we have sodium. It's losing an electron, and now it's become a positive ion. So if sodium always has, oh, and this is where I need my PT table.com. Let me find it in my notes. I think it's 11, but like I said, guys, I don't have the periodic table memorized. I see some pretty often. I kind of have them memorized. Okay, sodium, it is 11. So sodium always has 11 protons. So if we count here, 1, this is, okay, so its protons are hanging out where the Na is listed, right? They just assume that we know there's 11 there. But here's their electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we were to do P minus E, 11 protons minus 10 electrons, that is 1. 1's a positive number, right? We didn't get a negative number. And so therefore it's a positive ion. If we were to do this again, and for some reason we were to get 12 electrons and get a -1, then we would have a negative ion. Okay. So, OWL has a question where you fill in this chart. This is OWL question 9 and 10. That I don't remember specifically. I think it's specifically question 9, but this relates to question 10 as well. This is the same concepts. I liked this table though. Okay, so using what we know, right? We know that the atomic number equals protons. We know that the mass number equals P plus N. We know that the charge equals P minus E. So if we're only given, a few things, we can figure out everything else here. Nuclear symbol, that's what I was, the notation that I was describing earlier here. I forgot the name of it until I just saw that there. Okay. So, element that has an atomic number of 3. So if I go to the periodic table and I look for the element with the atomic number of 3, which also happens to always equal the number of protons, so I can go ahead and fill in 3 here, happens to be lithium, Li. And so they gave me the number of neutrons. And so mass number, P plus N, 3 plus 3 equals 6. I'm skipping the nuclear symbol for now, I'll come back. Now it's already telling me that this is a neutral atom, and so therefore its charge equals 0. So if this were to be a charge of 0, it means that the P minus E equals 0. And if in this case my P is 3, well, then my E must always be my electrons must must be 3 in this case. So if I wanted to fill in this nuclear symbol, right? Lithium. So on top is the mass number, which we already filled in, 6. And then on bottom is the atomic number, 3. So when you're putting this into OWL, you like click on it and then it kind of brings up this box of all kinds of little choices. Choose the one that says X and then it has a box on top and bottom. So when you click that and you start typing in LE, that will appear where the X is. And then you kind of have to like click in this vicinity to put in 6 and then click in this vicinity to put in 3. It's a little tricky, but hopefully you guys can get it. All right, doing the second line here. The element symbol, it's already given to us here in the nuclear symbol, right? Atomic number corresponds to that bottom number of the atomic or the nuclear symbol, so 3. And it always has to equal 3 if it's lithium. Mass number corresponds to that top number in the nuclear symbol, so 7. Now, if it's lithium and its atomic number is 3, it always has to have 3 protons, right? Because this category equals this, and lithium is always going to have 3 protons. That's what makes it lithium. Neutrons, right, was P plus, oh, I'm sorry. That's not what I want to write. I wanted to inverse this formula. Okay, so mass number is always P plus N. So therefore neutrons, if we were to like, is going to equal mass number minus P. So we have mass number and we have P, so 4. And if it was a neutral atom, it would have the same number of protons as it does electrons, and therefore 3. Okay, doing the last line here. I'm going to skip the nuclear symbol till we fill out all these other boxes. So cobalt Let me go to my periodic table again. We'll figure out its atomic number. This might take me a minute to find on the periodic table. Cobalt. Okay, 27 is its atomic number. Its atomic number always equals its protons. And, oh, I guess I could have just solved it without looking at the periodic table. If I would have done a neutral atom has the same number of protons as electrons, I could have got it there. But, you know, there's so many ways to work about this table, right? Okay, so our mass number is 59 in this case. And it equals P plus N. Our P here is 27. So if I were to subtract, N would equal, and I don't know this math in my head, give me one sec. $32. Okay, so I'm ready to fill in my nuclear symbol. So cobalt, the atomic number, or same, atomic number goes on bottom. And then the mass number goes on top, which is 59 in this case. Awesome. Cool. All right. All right, so now we're talking about the mole. So what the heck is a mole? It's not the fuzzy thing that's in the ground, although that is technically a mole. Mole is also known as Avogadro's number, sometimes denoted as Na. I wish it was An. I don't know why they did that. Why would you put the N first when it's called Avogadro's number? I don't know. But basically, it's just an amount. So think about like a dozen eggs, right? We always know that equals 12. A pair of socks always equals 2. A mole always equals 6. Oh, this is an error. It always equals 6.02. And here's the full one. We can always just call it 6.02 for our purposes, times 10 to the 23rd. That's so weird that little graphic has an error. Okay. So a mole, right, just like a dozen, always equals this number. So when the heck are we going to use this? Well, it comes into play for molar mass. So basically the periodic table, we have the mass number, which was based off of the specific number of protons, any neutrons, but on the periodic table is what's listed as the molar mass. And this is the average of all the masses. Remember I said this on another slide, of all the isotopes that exist. So basically, some person somewhere decided to discover how many isotopes there could be, how abundant they were in nature, and take the average of all of those. And so that's the number that we see on the periodic table. And so this is based on a mole. So if we were to look at carbon, right, its molar mass, the number listed on the periodic table, is 12.01. Might be a little different based on what periodic table you're looking at, but that's fine. This same number sometimes is called average atomic mass. It's more derivative of its exact definition. It's sometimes referred to in the units AMU and sometimes referred to in the units grams per mole. Both equal each other. For our purposes, let's remember grams per mole moving forward. How many moles? In 1 mole of the mole of carbon, there's always going to be 6.022 times 10 to the 23rd atoms. If we were to look at the periodic table and do the same thing, in 1 mole, the mass listed on the periodic table is 1.008, but it still only has 1 mole of atoms in it, therefore Avogadro's number, and so on and so forth. Again, these numbers sometimes vary based on what periodic table you're looking at. Sometimes this is 15.999. You might think to yourself, oh my gosh, which periodic table should I use? Don't worry, because once you do the calculations, whatever OWL or the exam, they're all gonna come once you round them and stuff. It's gonna be this using 15.99 or 16 is like using the same number basically. I mean, don't get too crazy with your rounding. I wouldn't round this to just 35, but you know, you can round 3 nines to 16, and the same you could probably round sodium to 23. Okay, so in class we talked about the factor label method. Let's apply that with the mole. And oh my goodness, we're about to get more intense with our factor label method. So like we said, 1 mole always equals 6.022 times 10 to the 23rd atoms, or particles, same thing. Or even molecules, same thing. It equals 6.022 times 10 to the 23rd stuff, basically. So if we were to be asked how many moles are in, you know what, I actually want to skip ahead to a different slide real quick. Okay. Okay, here, this is a better example before I get into those other examples. Okay, so this is question 11 of your OWL. So how many moles are in boron tribromide? So how many moles are present in this amount of molecules of this compound? All right, so factor label method, right? Start with the number that we're given. 5.13 times 10 to the 22nd molecules. So we want to get out of molecules and into moles. Now I just told you that Avogadro's number this is so 1 mole equals that many molecules, or if it says particles or atoms, it all means the same thing. So basically I can just put in 1 mole on top and Avogadro's number on bottom for molecules, and I can do the math, and I am left with moles. All right, how many sig figs did I know how to use? Well, I was doing a multiplication and a division, basically. Multiplication, division is the same rule. We want to go to the least amount of sig figs. This only has 3 sig figs, regardless of the times 10 to the 22nd stuff. Here's 4 sig figs. So multiplication division rule is to use the least amount of sig figs. So leading zeros never count. So we start counting here, 1, 2, 3. So our answer, all right. The second one, how many molecules are present in 4.91 moles? So factor label method, start with what we're given. Put what we're trying to cancel on bottom, what we're trying to get to on top. If we know the conversion factor, which we do know from moles to molecules. So 1 mole equals 6.022 times 10 to the 23rd molecules. Same thing, 3 sig figs here, 4 sig figs here. And when I do the math, depending on what your calculator, how many decimal places you have set to your calculator, it might give you this number in a crazy big formula. But my calculator automatically put it in the exponent. And I will accept it either way. If you want to use the exponent, if you just type the x, lowercase x, it will automatically fill in this with a caret, and then you just have to type in 24. Alrighty. Let's do the next practice problem. There it is. Okay. So this is still relating to the mole, but this time using grams. So let's go back to that other example I was trying to show you earlier. Okay, here. So we know that 1 mole equals Avogadro's number, which, molecules, particles, atoms. And we just learned about the molar mass, which is a way of relating grams to moles. And this is found on the periodic table for each element. It's unique to each element. So doing this practice problem here, factor labels. Start with what we're given, 4.97 grams of potassium. So it's asking us how many moles. So we want to get out of grams of potassium and into moles of potassium. So we do have a way of doing this. The molar mass, which, like I said, is unique to each element given on the periodic table. So when you look up the molar mass of potassium, it says 39.098. And so how you read this, because sometimes it doesn't always say the units, even though we stress how important units are, right, is grams per mole. So this number always sticks with the grams, and 1 always sticks with mole. All right. So if we were to do the math there and use sig figs, this comes out to 0.12 moles of or potassium. If we wanted to do another example here, we're looking to figure out the mass of a liter of air when a liter of air equals that number of moles. So factor label, let's start with what we're given. I don't know why I put a 0. Where did that? Okay. Erase. Okay. Argon. Argon. So multiply by a conversion factor to get ourselves out of moles of argon and into grams of argon, which we do happen to know based on the molar mass. So this is always going to be 1, and then this will be the number that we find on the periodic table related to argon. And the periodic table I was looking at had this, and I just felt like copying it all. This doesn't really matter how many sig figs you get from the periodic table, because usually this number is always the limiting one anyways. Okay, so when I do the calculations and I go to only 2 sig figs, I get this many moles of argon. Okay. So do this, and then we'll take a little break because it will move into chapter 3. All right. So 13. Okay. So A, how many moles of nitrogen atoms are present in a sample that contains 4.91 moles of dinitrogen monoxide? So here we want to get to moles of nitrogen, and we're coming into moles, or we're coming out of moles of Na2O. Now you might be thinking, wait a second, we haven't learned this. But like I said, there's always 1 mole in every, remember that graph I showed earlier where it said carbon always equals, 1 mole, and then it was like, I kind of forget the other ones I listed. I think oxygen was on the bubble. So whenever we see the element, right, that's always 1 mole unless designated otherwise. So in 1 mole of this compound, how many N's are there? Well, we would defer to 1 unless denoted otherwise, and it is denoted otherwise as a 2. So we would do the math on this. I would have to plug this in my calculator. 9.82. Okay, so there's an example of A. B, how many moles of N2O molecules are present in a sample that contains 5.37 moles of nitrogen atoms? So start with what we're given. Moles of N. Now this time, we want to get out of moles of N and into moles of this compound. So in every 1 mole of the compound, there's 2 moles of N. So we take this number and divide it by 2. So let me put that into my calculator. So my calculator is giving me 4 sig figs, but I'm going to only go to 3 here just because that's what was given. Okay. So here's this third problem I was looking for. Okay, I believe this is question 13. My apologies. The one before that was question 12. Or, you just have to look. I'm a little confused myself. Okay. All right. So now we're going from grams to moles, just like that other example that we did using the molar mass. So 2.86 grams of the given compound. We want to go from grams of this crazy compound to moles. Do I know how to do this? Yes, molar mass. Anytime we want to go from grams to moles or vice versa, equals molar mass, which we find on the periodic table. So that number always corresponds to 1 mole. And so, oh, I remember why. Okay. I remember why I did this. Okay, so this is so complicated. I hate that they did this to you. Okay, so just for now, Google the molar mass. Literally type into Google molar mass of BBr3 and get the molar mass and put that here. This is why I took away that problem, but I want you to do it this week. Okay. So now we're out of grams of BBr3 and into moles. of BBr3. And I know I don't have the exact thing. I'm sorry. I'm using my computer and my iPad for this recording. And therefore I can't Google what it is. But I promise whatever your compound is, just for now, we'll talk about how to calculate it. But for now, Google molar mass of whatever compound it is. Make sure you put that with your grams, because that corresponds to 1 mole of that compound. So B is the similar but going the opposite way. So 4.90 moles of BBr3. And we want to go to grams. So we want to get out of a compound on bottom and into grams on top. 1 always corresponds with the mole. And again, whatever this you Google is the same here because it's the same compound. Put that there and do the calculation. So you're multiplying 4.90 times molar mass, and that will be your answer. All right, so next video will be chapter 3. All right, chapter 3, the periodic table. So we've already kind of introduced the periodic table a little bit. So this will go by pretty fast. So we kind of talked about why the group's the way they are, but early chemists basically decided, we're going to group these all on their atomic masses because that's the only correlation they could find. But as they started doing that, they realized that they were also grouping them based on their physical and chemical behaviors and properties. So those same properties that we talked about in the very beginning of lecture yesterday. And so soon they realized not only were they organizing them based on atomic number, that they no longer were really focusing on the mass, even though sometimes they did have a correlation. Obviously, helium weighs more than hydrogen, but there are some outliers. If you were to look at the atomic mass, for the most part it increases, but there are some outliers. But you don't study the periodic table. So the modern periodic table looks like this, where we have periods, which are the horizontal rows, and groups, which are the vertical rows. So this is a group, this is a period. And so we can look even further into this and divide the table into these different categories. So group 1 is the alkali metals, group 2 is the alkaline earth metals, 17 is halogens, 18 is noble gases, blah, blah, blah. What you should pay attention to here, transition metals are that group in the middle, and noble gases are this last row. Those are the two big ones. So noble gases, right? This is maybe something that you've heard before. Noble gases are in this last row here, and it's things like helium, neon, argon, xenon. I don't know if I'm pronouncing that right, but they're these gases that stand alone. They hate making bonds with each other, and they're very explosive, very reactive, right? So if they just hang out by themselves, they're happy. So another word that they like to use commonly in chemistry is that these are inert gases. Another thing is these always appear as gases. That's why, obviously, noble gas. They always appear in the state of matter of gas. So looking at the periodic table again, there's a little bit more of a zoomed up view. We have this other row down here. I wouldn't stress too much. These are just additional transition metals that were found kind of later. And sorry. Stop. They were found later, but then were also found to have properties that were in between 56 and 77, based on their weight and stuff and their protons. Anyways, what I wanted to show you, we can divide the periodic table into metals and non-metals. So usually there's a line or there's this box, colored boxes here, whereas these are the non-metals, and these are the metals. With the exception, hydrogen hangs out here, but he's actually a non-metal. And you can tell he's colored green there like the other non-metals. Don't worry about memorizing where this line is. Do not worry about memorizing. I do not have that line memorized. Because in most periodic tables, it's designated by colors. And if you get a black and white periodic table on the exam, it'll be this like thick line or something. All right, so metals and non-metals, very important to remember going forward. So one other thing I wanted to show you here is this periodic table. So the periodic table I just been showing you was more, I would say modern view. I got it from another textbook, where it had periods listed as 1, 2, 3, 4, 5, and groups as 1, 2, 3, 4, 5. Previously, the groups had these Roman numerals 1A, 2A, 3B, stuff I don't understand why they were named that way. But I'm just showing you this as a reference. Basically, don't think too hard about it, because OWL does have questions where it references, group 2A. So here's just a periodic, if you get confused, here's a periodic table which uses those. Something else I kind of liked about this periodic table too is it has those groupings, the alkali earth metals, the transition metals, all that stuff colored, as well as the line here for gases and noble gas, or I'm sorry, metals and non-metals. So if you like this periodic table better, there you go. There's another way of looking at it. While we're at this periodic table, though, let's talk about another trend. There's this other trend up among the periodic table in which the electrons are organized. And so we might previously know that every element wants 8 electrons in its outer shell. 8 is the magic number. Sometimes, though, they don't have 8. In the case of the noble gases, they do have 8 in their outer shell, but all the other elements don't. And so they commonly have to form bonds with other elements to get 8. So there's this trend where hydrogen only has, and all the other elements here only have 1 electron in their outer shell. 2, skip the transition metals. 3, 4, 5, 6, 7, and 8. So oxygen has 6 electrons in its outer shell, and so does all the other elements in that group. So there's another trend that we can match here. I'm going to use blue, where I'll use plus as I'm willing to give it away, and minus as I want. So hydrogen, lithium, anything in this first group, they are going to want to get 7 electrons to make 8. It's easier for them to just give away 1. When we look at the second row with magnesium and calcium, they could take on 6, or they can just give away 2. Skip the transition metals. It'd be easier for them to give away 3 than to take on 5. Carbon, this row here is a little bit tricky because they're kind of in the same, we could give away 4 or we can take on 4. Doesn't really matter, that's the same amount. But as we start to get to the rows to the right of 14, they start to want electrons. So you can think of the minus being they want that many electrons, or they're that many electrons short of a full outer shell. The pluses as being they're willing to give away that many electrons, or that they have that many electrons in their outer shell. Specifically, this periodic trend of electronegativity. Electronegativity, I wonder if I have another periodic listed. Okay. Electronegativity is, and I like to abbreviate it EN, is basically a trend that measures how bad you want electrons. So if we look at the periodic table, the trend of electronegativity increases as we go to the right and increases as we go up. The noble gases are the exception to this trend. Fluorine is going to be our most electronegative atom. He wants electrons, right? He's only 1 away from giving a bond, from getting a bond. You know what? I am so sorry. Now that I look at these, I should have listed plus as giveaway and negative as 1. Because if he's 1 away from creating a bond, he really wants electrons. Whereas hydrogen, he'll give that electron away because he's 7 away from creating a bond. That makes more sense. Yeah. So there's another trend that goes to the opposite corner where you increase as you go down and increase as you go to the left for atomic radius. So atomic radius is just the size of the atom. So fluorine up here has a really small atomic radius, and Fr, which I don't know the full name of, he has a very large atomic radius. And if we were to work backwards, try to determine boron, he would have a somewhat larger than fluorine, but smaller than, say, magnesium, because magnesium is closer over here. Okay. So we just talked about wanting electrons and giving away electrons, all in hopes of making molecules, right? So we kind of introduced looking at molecules earlier, right? So these all have bonds between them in which they're sharing electrons. And one of them either had to want some electrons or give away some electrons. So the octet rule, right? The magic number is 8 electrons. Every element wants 8, which is considered a full outer shell. So what do they do when they don't have 8? They'll make a bond with another element. And so they'll give their electrons to him. Maybe he gives some electrons to him, and they'll orbit in a shared manner, and they'll hang out, basically solidifying that they're always going to be together because they've formed a bond. So this picture shows covalent bonds, which means there's a physical bond here. They're sharing their electrons. Physical bond. You're gonna find them hanging out together for sure. An ionic bond, I put bond in quotes because I don't really like that they call this a bond, is where they straight up give away electron. So here's sodium, right? We talked about him having a +1 charge. He wanted to give away 1 electron. He's giving away to chlorine, which we talked about had a -1 charge, which really wants electrons. And so now sodium, he's 1 electron down. So if we were to calculate his charge, he would have a plus charge. He has more protons than electrons. And chlorine now has more electrons than it does protons, so he has a negative charge. There's no physical bond here. Those electrons aren't orbiting together, but rather this plus and minus is making them attracted to each other, right? Opposites attract. And so we're going to find these in space together, but it's not necessarily that they're physically bonded and that their electrons are orbiting. So transfer of electrons. We'll talk about ionic bonds a little bit more later, but I had to kind of introduce it a little bit because of, again, your Labster, and it makes the periodic table make a little bit more sense. So finally, this is an OWL question, specifically 16. And this question is asking us to look at the periodic table and look in group VB or group 5 and period 4, and we're going to find the element V. I don't know what V stands for. And not asking us necessarily to put that element here, but to tell its corresponding atomic weight, which in this case is 50.94. So your groupings might look a little different here, so you might be searching for a different element, but the question is basically, can you search the periodic table? If we were to look at group 16 and period 2, that's oxygen, which has a atomic weight of, and remember, different periodic tables say different things. This specific question, if you do have oxygen, they want you to put 16.00, which is 4 significant figures, right? Because trailing zeros sometimes count if they come after a non-zero digit and a decimal, which it does. So I know it's tempting to put 15.99, but they want 16.0, just weird, quirky owl things. Okay. And then let's see here. If we were to keep doing this, we'd find copper. I think that's, yeah, copper. And we would look at the periodic table, its weight, it's 63.55. We were to search group 1, and remember groups are what's going down, periods are what's going across. We'd find RB, don't know what that stands for. And if I were to look at its periodic table, mass is 85.47 or 85.47. Okay. So lastly, I only wanted to cover this really quick because this is not something really heavy in this module, but you happen to have an OWL question on it. And this is OWL question. It's kind of early. I want to say it's like 4 or 5. Here it is. Oh, 15. My apologies. Question 15. Okay, so we'll see this a lot more next week, but for some reason, Al wants you to complete it by Sunday at, midnight. So percent composition, right? Percents composition, right? It's going to be the number of a specific atom, so the part over the total times 100. No units for percents. The percent sign is the unit. So it's asking us to calculate the percent composition for xenon oxide. I'm assuming that's oxide. What the heck does that mean? We'll discuss this. It'll make more sense next week. So basically, we need to figure out the total of xenon oxide. So if you want, honest to God, if you want to just Google molar mass, because we'll learn this next week. But if you really wanted to calculate it out, you need to look at the periodic table for the molar mass or the weight of xenon, which is 131.29 grams per mole. Oxygen, which I'm going to use 15.99 here, grams per mole. Now, there's only one xenon, but there's 3 oxygens. So for the entire molecule, I need to multiply 15.99 by 3 and then add it to the xenon to get the total weight of this molecule, which when I do the math, so that 3 though, that might be different based on your compound. It's whatever the subscript is. If there's no subscript, consider it 1. All right, so now it's asking me what's the percent composition of xenon. So now I have my total, right? I can plug that in for my bottom. My part, in this case, it's looking for xenon. I can just plug in this guy. I can multiply that by 100, do the calculation, I get my percentage, which round this only to 2 numbers, regardless of sig figs here, because it's always weird. It likes to change its rules halfway through. 73%. The mass percentage for oxygen. So again, my total is the same. I can put the same number on bottom. This time, I want to put not only 15.99, but and I'm going to use the word total here, but it's misleading, the total amount of oxygen, which is 15.99 times 3. So that is 47.97 times 100. So when I do 47.97, divided by 179.26 times 100, I get 27%. All right, don't think if this is confusing, we'll revisit it again next week. But I wanted to at least explain it to you so you have some kind of reference when you encounter this question on OWL. Okay, oops. So my last slide. I showed you this slide earlier, but I just want to give you a few more reminders. So you have 2 Labsters, which are that online simulation. You have to complete those by Sunday. You have your discussion post due tonight by 11:59, and that's your initial post, right? I have to tell you that it has to be 200 to 250 words. I get the autonomy of grading it though. If I see that you have put in a decent effort, you've answered the prompts, and you're not just saying, you're not just being short, but you're still short of 200 words, I'll still give you full points. If you've put in the effort, but you just happen to not reach 200 words, that's fine. I understand. The discussion posts for chemistry are a little wonky. All right, so by Sunday at 11:59, you want 2 responses. And put some effort into your responses, right? Not just, that's great, At least make them 1 to 2 sentences. There's not a word requirement for that, but if I feel like you've put in a good effort, I will give you the points. Also, so I said the 2 Labsters were due. Your OWL homework is due. And remember, your OWL homework also includes this knowledge check, which is basically 10 more questions that are similar to OWL concepts. I do have virtual office hours this Sunday. So there's a Zoom link in my original announcement from 7 to 8 p.m. Please come in and talk to me about the factor label method, significant figures, because those are very reoccurring and topics that really build on each other. Even the mole's hard, and they make me introduce it in the first week. So looking at next week, again, there's no in-person lab, same with this week. I also have office hours on Tuesday before we start class, 5 to 6, and those are in person in our class. So before you come to class, it'd be great to look at the readings. You could look at those videos. Those videos are great. They're nice little short, little kind of crash courses. It would be kind of helpful if you did look at the homework, but I'm not going to say it's required by any means. And again, you'll have a discussion post next week. So if you wanted to get that initial response out of the way, that would be probably beneficial. You'd be front loading a lot of that work. All right. Any questions, please feel free to email me. If I feel like there's a lot of questions over a certain thing, maybe I'll make another little video and post it to the announcements. All right.